Okay, well, good afternoon, everyone. Welcome to this session. I'm very pleased to introduce my colleague Luca Parisi, who today is going to tell us about building and installing packages with CMake, a hands-on introduction, and he's going to be doing some live demonstrations using our machine Cirrus. So take it away, please, Luca.
Thanks, Claire. So we'll now share my screen. Okay.
Yeah.
Perfect. So what we will be talking today is about CMake. So you can find this material on the webinar page. So there should be a link to the slides presentation, which I will be showing throughout this seminar. So let's start by what CMake is. So CMake is a tool to allow you to build packages from source code. So typically, if you're using an application on an high-performance computing machine, often packages are distributed as source code. So essentially, it's a bunch of text files containing the source code. And in order to use the package, you have to transform all these text files into an executable that you need to run. So packages can be large or complex. So this typically involves a lot of steps. So you need a way to record and reproduce all these steps on your system. So typically the package developer will create some kind of build system, like a Makefile, which is very common on Unix-style machines, Unix-style systems. And this will have a set of rules to create all the steps required for, typically first for compiling all these text files into object files, and then linking them together, and together with some external libraries on your system to generate the executable. The problem is that in this process, the build system needs to know about the user's environment. So it will typically use to know a compiler, and the developers will not know what compilers you have available on the system or where they are. Same with libraries. You often want to link with some system libraries, such as the vendors optimized versions of MPI, and the package developers do not know which library you have or where it is. So typically, if all you have is a Makefile, it's the user responsible for modifying the file or some custom configuration file and typing in which compiler they want to use, what location of the libraries, and so on. This is not a standard process, so it can be difficult to understand, time-consuming, and you're very likely to make some mistakes or error, which can be really hard to debug. So that's where CMake comes in. So CMake is not a substitute of Makefile. It's not a build system, but it generates a build system for you. So typically, the user will need to install the CMake tool, and then it will run CMake, and CMake will scan your system and figure out which compilers you have available, where they are, what libraries that are required to build the package you do have on the system. And once it has finished this configuration step, it will generate a build system. On a Unix machine, this is typically a Makefile. And this make file will contain all the information about what compiler you want to use or which library you want to use. So on ARCHER2, for instance, you might want to use the K compiler and the K MPICH library. You will not need to edit this make file. You just need to run it, and it will create the executable. So overall, what CMake is, so it's a tool that you can use as a user, is also a programming language, because the developers are responsible for creating some CMake code that essentially will tell the CMake runtime tool how to build the package from the source file and what it needs to be built. It's not a build system, but it generates a build system based on the configuration of the system the user is using. And it's also a way to abstract the build process. So in a makefile, you need to specify all the commands required to build, to compile the object files, to link them, and so on. You will also need to specify all the flags you need to pass into the compiler, which might depend on your compiler. Instead, CMake can do much of the heavy lifting. All you need to tell it is what you want to build, from what file, and you might want to set several properties to customize your builds, but you don't need to go in all the glory details. CMake can figure out most of those for you. So it's also a way to simplify building a package from the point of view of the developers. So the main advantage of CMake is that you get portability. So you can you can distribute your package, the package you're developing, and it can be built on any system. So CMake will support most systems, so definitely supports Linux, but also supports other operating systems like Windows or Mac. Supports more than one build system as well. Typically you will use Makefile, but it also supports Visual Studio and other build system. The main disadvantage is CMake has been around for a very long time, and over time it has changed and improved quite a lot. But unfortunately, it needs to keep compatibility with older versions of CMake, and older versions of CMake made use of a lot of practices, which are now considered to be bad practices, like heavy use of global variables and other features that are now kind of deprecated. While modern versions of CMake do not rely on these obsolete features, many CMake package developers still write packages with in mind these older versions, unsafe versions of CMake. So that can cause a lot of problems, which can be difficult to troubleshoot. And it also means that sometimes you may have a build is successful with one version of CMake, but will fail with another, which can make things more difficult. So now let's try some example. So what I'm going to do is to compile a very simple Hello World CMake package. So I'm currently in the demos folder in the material. So I will move to the Hello World CMake folder. So I will type cd hello _world _CMake ls. So you can see there's directory called hello world. So cd hello world ls, and you can see that there is a hello.f90, which is just the Fortran file will just print an hello world message to the screen. And there is also a CMake list.txt file. So this is what defines the CMake package. So let's move on the parent directory, so cd.ls. So in order to build the package, we first need to create a directory where to build it. So I will type make build, and I will move into the build directory. So cd build. This is the directory where we will build the software. So it will create all the executables, but also a bunch of files, a bunch of temporary files that are produced by the CMake build process. The first thing we want to do is to tell CMake where our source code is, and to configure the build process. So it will need to scan the system and find compilers and everything it requires to build the package. So first thing, we need CMake available. We can do that by loading the CMake module. So we can type module load CMake. On your own system, you might need to install this. So CMake is available in most package repositories, including, say, apt if you're using Ubuntu, or whatever is your favorite package manager for your distribution. So now we can type CMake. Then we need to specify where the source code is with _s, and then type in the directory which contains the source code. So /hello world. We also need to specify the build directory with $B and dot for the current directory. So enter, and voila. So what CMake now is doing is configuring the build process. So you can see that it prints some information on the screen. So it tells you that it has found a Fortran compiler, a new compiler, and then it tells you that it has tested it, that it works, tells you that it's done with configuring the package, and it has generated some build files in the current directory. So if you type ls, now you can see that the directory is no longer empty, and there's a bunch of files, including a make file. So this is the build system that has been created by CMake. Now, to actually build the package, we need to run that build system. So one way to do this is by typing CMake -- build, and then the path of the build directory, which is just dot. Alternatively, you can just run the make file. So by usual typing make, so enter, okay, and CMake has now built the system, has built the package, and create a hello executable. So I can easily run it. So /forward hello, and this brings hello world to the screen. So we also need to install, you might also want to install it. So at the moment, if we type ls, we can see that here we have the hello executable, but we also have a lot of other bunch of files that are only needed to build the package. We don't really need it to run it. So in order to install the package, we can copy the executable and any file that the package needs to be run on an install folder. So we can do that. We could do that by tapping make install. Type enter. Okay. So here it says install, but it's installing the project. So that it's installing, but then gives you an error. And it complains that it cannot copy the file to this directory. So user local bin hello. This is because by default it's trying to install on your main system. So, but you do not have root access. You typically do not have root access on HPC facilities. So we don't have writing permission to this folder. So you have to tell CMake to install the package in some custom folder. To do that, we can type CMake again. Now we will need to specify the source and build directory again, but that's a lot of flags, feeling kind of lazy, so don't want to write all that down. So an alternative way is to just give as an argument the source, the directory containing the source code. For instance, in this case, the source code is in the parent directory, so /hello world. And CMake will figure out that this argument is the source directory, and will assume that the build directory is the current directory, which in our case is currently correct. Then we need to tell CMake in which directory install the package. So the way you give information to CMake is typically by defining some variable. So variable can be defined from a command line by typing /d for define, then the name of the variable. Now the variable we want to set is CMake _ install _ prefix, and we'll set equal to the directory where we want to install the package. So for instance, we may install in the parent directory /hello install. Run it again. So type enter. Okay, so it says configuring done, generating done. Let's type make again. So it's not doing anything because it doesn't need to rebuild the package. Everything has already been built. Now let's type make install. Okay, this time there's no longer any error. And it does say that it's installing to the directory that we provided. So let's check if it's actually there. So cd parent directory cd hello _ install, type ls, and you can see that CMake has created a subfolder called bin. Move into the bin directory, so cd bin ls, and here is your executable. So we can run it and work. Now, of course, this is very easy. A very simple package, just linear hello world to the screen. So everything just works out more or less out of the box. If you have ever used CMake, you probably had a different experience. Most of the time, you're given a CMake package, run CMake, and then issues arise. So let's try now to build something a bit more complicated. So we return on the demos directory, so cd ls. Okay. So here we have another directory called WinTunnel. So this contains the source code for a simple simulation of wind flow around a wing. It doesn't really matter for us what it's doing. All we're trying to do is to compile it. So first of all, we need to create a build directory. So a temporary directory where to store all files that are generated by the build process. So let's start make dir build underscore wind underscore tunnel. So let's cd to the directory. So cd build wind tunnel. ls. Okay. Empty directory. So let's try again to call CMake. So CMake dot. This is a short for telling CMake the source file is in the directory parent directory /windtunnel. We don't need to specify the building directory because it would just assume that it's the current directory. And let's type enter. We'll try to compile, print some information to the screen, and fails with an error that no CMake CUDA compiler could be found. This is because the package is by default supports GPUs, but on this system we don't currently have a GPU and no CUDA compiler available. So of course they cannot find one. So what we want to do is to tell CMake, do not try to use CUDA. Do not build with CUDA support. So the way you tell things to CUDA is by defining variables, but we need to know which variable we have to define, and that will depend on the package. So in order to figure out which variable we need to set, we can call CMake again, same argument as before, but we add a dash L for list. This will print all the variables that the developers expect the user to change. And then we also add H. This will print also some helper strings, so some comments that help the user figure out what the variables are for. So type this, enter, and you can see that it has printed a bunch of stuff to the screen. So you can see that this variable called CMake build type, which is a string, and by default it's set to release. So this is a variable which is defined by CMake itself, not by the package developers. And essentially what it tells you, it sets the optimization flags. So when you set it to release, it says that the package should be built with optimization flags turned on. So the package developer does not need to specify directly the flag. You can let CMake do it for the developer based on the compiler that you're using. We've encountered this variable before. So this is CMake underscore install prefix. And this is the directory where we want to install. So by default, it will be installed in user local, which of course we have no permission to, so we will need to modify this. So the next options are how to select the GPU hardware, but we're not going to use GPU, so we don't need it. Then there is an option to whatever we want to build or not test. And finally, there's an option to turn CUDA support off. So it's this variable called useCUDA. It's a logical variable, and by default it's set to on. So we can run it again. So type -d. So let's define all the variables that we need. So we can type CMake underscore install prefix and set it equal to, say, parent directory /forward and wind underscore tunnel underscore install, and then /d use CUDA equal off. So this will take CMake to not build with CUDA support. So let's run it. Okay, it's tempting to configure. Oh, I have forgotten the LH flags, so it's not actually compiling. So let's remove them. And run it again. Okay. So again, we see an error. So it says that it could not find MPI Fortran. That's because we don't have it in environment. So let's say we want to use OpenMPI. So we will load the OpenMPI module, run it again, okay. So now it says it just found the MPI Fortran, and it says the path of the library, which is our OpenMPI library, so which is what we expect, and build files have been written. Notice that this time we get much less input. That's because once CMake has defined a variable, when it has found a compiler, it's not going to look it up again. So that means if you want to start from scratch, you need to remove all the temporary build files. Otherwise, it will not try to reset those variables again. So let's see if we can compile this time. So let's type make. And yep, and everything is compiled. Let's type make install. Perfect. So no error. Let's see if it has actually been installed. So ls windtunnel underscore install bin, and you can see that there is an executable. So it has been installed successfully. Now we just have so far we have let CMake find the compiler for you. And well, this time we're going to try to compile with a different compiler. So we're going to try to use the Intel compilers and the Intel MPI library. So let's move out of the build folder. So cd ... type ls. Let's try to build another build folder. So say build underscore Intel. Let's move into the directory. So cd build underscore Intel. Let's load the Intel compilers. So module load Intel -20.4 compilers. Okay, that worked. And then let's also load MPI. So module load Intel -20.4 /forward MPI. Okay, so now so if we type ls empty directory, so let's invoke CMake again. Now we still need to set all those environment variables, quite a lot, which you might not remember what they are. Fortunately, CMake offers an interactive interface to set variables and to discover them. So instead of typing CMake, we can type CMake. And then same arguments as before, so the source directory. So /win_tunnel. Okay, so this program appears to the screen saying empty cache, and we can type C for configure. So this will run the configuration. Okay, we try to find the MPI, but fails because we have not set, we have not told CMake to not use CUDA. So now we type A to exit the message screen. And this time you can see that there's several variables appearing on the screen. So these are the same which we saw when using the LH flag. So we can change the CMake build type, and we can switch between different variables by tapping up and down arrows. So we can go down all the way to CUDA, set it off by just tapping enter, then type configure again. Okay, I will type it again. Okay, and now it gives you the option to type G for generate. So this will actually generate the build system. So type G, we're back to the shell, and if we tap ls, there's a make file. So now let's run it. So let's type make. Now this time I want to see what commands make is actually doing. So you can do that by setting the additional option variables and setting equal to 1. So let's type it. Okay. So it's compiling and it's printing to the screen all the commands. However, if you look closely, you can see that it's not using the Intel compiler. Instead, it's using the normal new compiler. This is because we haven't told CMake which compiler to use. And it has just silently picked the first it found, so the system compiler. But we want to use Intel MPI. To do that, we can do that by typing, by setting an environment variable. So the easiest way is to just type export, the name of the environment variable we want to set. For the first-time compiler, this will be just fc, and set it equal to the compiler you want to use. For instance, MPI ifort. So if you're using MPI, it's usually best to tell CMake to use the compiler wrapper. In this case, it will be MPI ifort. On ARCHER2, it will be the usual Cray compiler. And CMake is usually smart enough to figure out that it's a compiler wrapper, and it's able to unwrap it and figure out which MPI you're using, what flags you need, and so on. So we set the environment variable, and we can run CMake again. Okay. Now we can see that it doesn't seem to have done anything, doesn't say anything about compiler. That's because CMake preserves the value of environment variables between runs. So once it's found a compiler and set the proper variable, it will not update it again. So that means you have to start from scratch. And the best way is just to remove everything in the build folder. So let's just type rm recursively all. Okay, so now I want to run CMake again. So we run the same command as we have before with all the variables. Type it. Okay, perfect. So it's doing the configuration, and you can see that this time it has correctly identified the intercompiler. So let's see if that's actually true. It's actually using the intercompiler. Let's type make verbose equal 1, and it's printing. So it seems to have compiled. Let's look which command use, and yes, you can see it actually used MPI fault when compiling. So it did use the compiler we told them to use. And yeah, we can do make install, and it will install it to the folder we specified before. Now, sometimes you might want to tell MPI and to tell CMake to use a version of the library which is maybe not in a standard location or on your path, but it's custom built library you have somewhere. So now what we're going to do is to recompile this once again with the new compiler and OpenMPI, but this time without using the compiler wrapper. So we assuming that we're using this, we just treat MPI as a external custom libraries, but it's not on your path. So I'm going to create a new terminal just to reset my environment. Move to the demos folder, type ls. So here let's type another build folder, so build OpenMPI _ OpenMPI. Okay, let's feed in the folder, so build _ OpenMPI. And once again, call CMake. First we need to load it, so module load CMake. Then type CMake. Once again, we type in as a first argument the directory which contains the source code, so // wintunnel. And the usual variable, so we have to turn CUDA off, so define use CUDA equal off, and set the install path, so define CMake _ install prefix equal to say // wind _ tunnel OpenMPI install. Okay, let's run it. Okay, it's finding the right compiler, but cannot find MPI, and that's because it's not on a path. So we want to explicitly tell CMake where it is. So this is typically very useful because often CMake may not be able to find bytes where your very specific packages. So in this case it's MPI, but in another case could be, say, a custom implementation of an input-output library, for instance. So the way to do this, the standard way to do this is to define yet another variable, so _d, and the variable we want to set will be the name of the package, in this case MPI, _ root, equal to the directory which contains the package. So I'll point it, this was not what I meant. So I'll point this to the directory that contains OpenMP or OpenMPI implementation. So this would be mount lustre hindi sw OpenMPI 4.1. Okay, so I'm going to run it. Okay, hello again. So what happened here is that when CMake is trying to find a package to find MPI, it calls a routine called find package and name of a package, in this case MPI. And in newer version, it will look into the variable called name of a package underscore root. But unfortunately, this is only to newer version of CMake. And by default, CMake will preserve the old way of doing things. So it gives you a warning about policy CMP 0074. And then goes on explaining that this feature is not enabled. So one way to go around this is to go into the CMake file and explicitly set this policy to the new behavior, and then CMake will use the MPI root underscore root variable. Another way is to use another way to telling CMake where the package is. So find package will look for your package in a lot of directories, and while they're well specified, it looks in a lot of directories and it's quite complex for historical reasons. So instead of defining MPI roots, for instance, we could define the variable CMake underscore prefix underscore path, not prefix, but path. So this will tell CMake that whenever it encounters a find package, look into this directory as well. So let's see if this one works. And it didn't because we forgot to remove the build files, because once a variable is set, it's not going to be changed again. So let's remove everything in the build folder and run CMake again. And this time it has found MPI. You can see links to OpenMPI. And let's see if it actually builds. So let's type make verbose equal 1, enter. And you can see that it's building. And if you look at the flags, you can see that there are several references to OpenMPI. So it's actually building against OpenMPI as we wanted. So you may have noticed that one of the solutions possible was not to change the variable, but changing the CMake file. And unfortunately, sometimes you do, in order to troubleshoot a problem, you might need to modify the CMake files. That's because packages are not always written with the best practices, or with or developed for newer version of CMake, but built for older version of CMake. So it's not so uncommon that you need to actually open the CMake code and look at it. So we'll return to the slide and look at the writing CMake package. So you can see, so the main concept of defining how CMake works is by defining targets. So a target is an output, so it's something you want to build. For instance, it can be an executable. Then you need to set, in order to tell CMake how to build it, you need to set some properties for the files. For instance, you have to tell it what are the source files required to compile to generate the executable by defining a source properties for the, in this case, myexec target. You also need, if you need to link with external libraries such as MPI, you also need to specify a library property for the target. And finally, you need to you also need to set up your project and tell CMake which version of CMake you want to use and which languages you're using. So as a short example, let's have a look at a very simple CMake file. So so in the demo folder, we're going to look at our hello world example again, but this time with MPI. So hello world come. So with CMake file. So let me give some more space. Perfect. So this is a CMake file. So it starts by, so just built an hello world, but parallel one. So it prints one hello word for each MPI rank. So first thing, define what is the minimum version of CMake that you wish to support. Then you define the project. So you define the name of your project and specify which languages you're going to use. In this case, all you're using is the Fortran language. Then we need MPI. So here it's where we call the find package routine. So this will look in a set of folders to look for MPI. It's quite complex where it's looking for things. So if you want to understand it, the best way is to just to look at the documentation. It's quite complex because it has different modes. There's a module mode, a config mode, and it will look for different files depending on the package that you want to find. After that, we define a target. So here we create an executable. So we will use the add executable function, and which takes as input the name of the target, name of your executable. And then we specify the sources property of a target. So we use the target underscore sources function, which takes as argument the name of a target, and then as last argument is a list of files which you want to compile in order to generate the executable. So in this case, it's just this Fortran file, hello.f90. Before the list of files, there's the declaration private. So this means that this property is required to build the target hello, but it's not required for other targets that depend on hello. So if you define another target which depend on hello, this property does not get forwarded. This is because the source file is only required by the executable. Then we defined the link library's properties for the target. So target underscore link underscore library. Take as input the name of the target. This MPI double colon MPI underscore Fortran. Now this is actually a target generated by fun package by the fun package command. So it's in itself a target, and this represents the linking with MPI library. And before that, instead of saying private, this time we said public. So this means that any other target that depends on hello will also link to MPI Fortran. And finally, we use the install command. So this defines which targets need to be copied over when you type make install. Of course, this is a very simple case, so we only have one target called hello. And that's all it's needed to write a very simple CMake list, CMake package. So it's useful to know the value section because you sometimes might need to modify subsection it, even if you're not writing your own CMake package. So this is pretty much everything I wanted to talk about CMake today. So there is more material in the documents which we didn't have time to go through today. In particular, let me point you to the resource page, which has different links to additional material, which can be useful if you want to dive a bit deeper into CMake, for instance, on not just how to use it, but also to write packages. So this is good time for question now. If you have any.
So there was a couple of questions in the chat, Luca, if you're able to knock that chat.
Yeah, I didn't see them. So is it enough to set an environment variable called FC and CMake picks it up? Yes. So there are various ways to change compilers. In CMake, there's usually 10 different ways of doing the same thing, but this is one of the easiest of the easiest way. So FC for the Fortran compiler. If you use the C compiler, you need to use CC for C++, 6.6, and so on. So on the material, you can find what those variables are, or you can find that information as well on the main website of CMake and the documentation. Set a typical default system environment variables for compiler. So it depends on the kind of default, but it will depend on your system. For instance, we use Intel, and Intel Fortran, the compiler name is it's not FC, right? It's MPI Fort. And if you on ARCHER2, it will be FTN, which is standard for the Kali programming environment, but not for other compilers. But yes, it's standard also in using Makefile, or Makefiles will, well, if you're lucky, they will honor that convention as well. How would you characterize the main differences between CMake and AutoConf? So CMake and AutoTools kind of are similar in the sense they try to solve the same problem. I would say the main difference is, well, ARCHER2 is harder to understand than CMake. It has its own way and non-intuitive way of doing things. So I would say it's, the learning curve is harder for CMake. And the other thing is, ARCHER2 has support for Linux, and can create makefile, but that's about it. While CMake can support not just Linux, but also other operating systems and also several build systems. So that includes makefile, but also other build systems like Ninja or Visual Studio. Are you familiar with CMake, which is used in building open form? Is this the same idea as CMake? How is it different? So I think CMake is kind of the open form custom version of CMake, if you want. So we used it before, but that is not like, it's like specifically tuned for the open form package, while CMake is like for any package. So it's meant to be a standard build process. So I'm not really familiar with CMake, but I understand that it's more like specific to this open form package. How do you know which compiler is the fastest or the best for the software you want to compile? Well, so I guess this is, well, this of course does not depend on how you build it. So it should not depend on what tools or build system you use. It will depend on your compiler. Generally speaking, the answer is try it. You never know which compiler will be better, will perform better or worse. So you would expect that the vendor's compiler will work best. Like for instance, on ARCHER2, you probably may expect the K410 compiler to be better, but this is not always true. So it depends heavily on the software you want to use. For instance, K historically has been good with vectorization. So if you have a code that can gain a lot by proper use of vectorization, and the K compiler might be faster than other compilers. But in other situations, the new compiler might be faster. So the easiest way is to just build both ways and try. Yes, I just saw it. You're right, Madden. So another alternative way to define the compiler is not to use environment variables, but to define a variable to CMake called CMake_Fortran_compiler. That's a good example of how in Fortran you can do things in lots of different ways.
Okay, I'm not seeing any other questions, and we are right up to the hour. So I'd like to thank everyone for attending. I'd like to thank Luca for an excellent and fascinating presentation, and to say again that this session has been recorded. So the recording will be added to the event page that you joined from, which also has all the materials and the slides that Luca has presented today. So thank you very much, everyone, and goodbye for now.